Welcome back. Welcome to Stochastic Methods for Engineering. We're going to go through just a couple slides to recap where we were. So this slide right here is just going to review the total probability law for point conditioning. So to get the marginal for y, get the pen. To get the marginal for y, you just integrate out the x's from the joint density. But the total probability law for point conditioning is essentially using the chain rule here for the densities, and again, integrating out the x's. And we can not only use the densities on the inside, but we can also use conditional probability here. Not just the joint, the conditional density, we can use a conditional probability. And to get to here, you just swap the integrals and you go. So, but today we're going to have some fun with casino problems. So imagine you come into a casino in Las Vegas and you have a wheel and you come to my table and the wheel is labeled uniformly from 0 to 1. The wheel is spun 2 times to generate 2 random variables, x1 and x2. The wheel is relabeled from 0 to x1 and spun again to choose a new random variable, y. The player wins if y is greater than x2. Find the probability that the player wins. So I'm going to go through and solve this problem in 2 different ways. So we'll have 2 different takes so you can see how to solve it 2 different ways. So I'll start right now with take one. Take one. So what do we know in this problem? What are we given? We know x1 is distributed uniformly on 0 to 1. x2 is distributed uniformly on 0 to 1. We also know something else about this problem. We know given x1 equals little x1, that y is distributed uniformly on 0 to x1. So given this, could anybody tell me what the conditional density for y given x1 is? Can anybody tell me what this is? For what range?
0 to x1.
Yes. Exactly. For y greater than or equal to 0, less than or equal to x1, 0 otherwise. So let's continue on. So we want to find the probability that the player wins. And that's equal to the probability that y is greater than x2. So right, with what we're given, we don't really know much, but what can we apply? Well, we can apply total probability to this expression. And we can simplify this, right? Because we know x2 can only take values from 0 to 1, so we can simplify the integral. And what can we do with this? This isn't quite what we're used to working with, but we can turn this into the minus f sub y of little x2. So we're integrating over an expression involving the CDF of y with argument little x2. So, well, we don't have the CDF for y, so what can we do? Any suggestions to get the CDF for y? Anybody know how we could obtain the CDF for y, or have a insight, some suggestion?
It's the integral of the density function.
Yes, so we have to get the density for y, and we can apply total probability 2 times to solve this problem actually. So we don't have f sub y of y. So we'll first find the density function of y. And we'll compute that like this. Right, because we have the conditional probability of y given x1. Does that make sense? Okay. So we can simplify this. We have the integral from 0 to y of 0 times 1, which isn't that interesting, plus the integral from y to 1 of 1 over x1 dx1 times 1. So that's just using the definition of the conditional density, and we can simplify this integral as the natural log, that's 0, but this integral right here from y to 1 of 1 over x1 is just the natural log of x1 evaluated from y to 1, which equals the negative natural log of y. So if we go back a slide, we're still hunting for the CDF for y, but we just got the density function for y. So what do we need to do now? We need to use the fundamental theorem of calculus, integrate from minus infinity up to a little y of the density function for y, some little v, some dummy variable. So simplifying, because y can only take values from 0 to some little y of negative natural log of v dv. So this, you may not know how to do this, but we can solve complex integrals using Sympy package. Show of hands, how many people have used Sympy package before to solve integrals? Anybody? Okay, I'll show you. I'll show you real quick how to solve this integral. If you don't know how to solve this one by hand, let's keep. Okay, can everybody see this? The code. So how you work with Sympy is we're going to say from Sympy, and this is just in a Jupyter Lite kernel, so it's very similar to your Jupyter notebooks you've been working with, but with this, like, it only saves it in your browser, so it's a light version of Jupyter Notebook. It's called Jupyter Lite. So we're gonna use the Sympy package to solve this integral. We're gonna start off with from Sympy, import symbols, and I'll explain what each of these mean in a second. We're gonna use integrate, and we need to use the specific Sympy math function. So we're gonna bring in the exponential function and the log function. So those are gonna come into the workspace. So we're going to use the y and v, and we're going to set up as symbols y and v. Now that we have symbols, we can compute the CDF for y pretty easily. How that works in Sympy is you use the integrate function on your symbols. But first, what you put into the integrate function is the expression you want to integrate. So we're going to use negative log of v, and we're going to integrate that over the v's from 0 to y. Let's see what that spits out. Let's print it, print the result. Whoop. So that's the answer. For what? Oh, okay. Full screen it. Does that help?
Oh yeah.
Okay, back to the slideshow. We'll come back to that. I'll try and make it bigger next time. We'll use it like 3 more times in the lecture. Okay. So this was negative. So this was negative v log v plus v, I think, 0 to y. And so if we simplify, the CDF is just y minus y log y for all y greater than or equal to 0, less than or equal to 1, and it's 0 for all y less than or equal to 0, and it's 1 for all y greater than or equal to 1. So now that we have our CDF, we can go back to our integral here, and we can plug in. So we want to integrate from 0 to 1. So the probability of winning equals the integral from 0 to 1 of 1 minus y minus y log of y. Actually, we want to use x2. And if you solve this integral, which maybe some of you all can do it by hand, but you can use Sympy to solve it, and you actually get a quarter. So, do you want to play this game in casino? Like you get a quarter chance of winning? Probably not. So we're going to solve it a different way now. So take 2. So in the first way of solving it, we use total probability 2 times. And we work with the CDF for y, an integral involving the CDF for y. But this time, we'll actually solve a triple integral, and we'll work with the joint density and do some manipulation on the full joint density on the 3 random variables, x1, x2, and y. So the setup is the same. So we have x1's distributed uniformly from 0 to 1, and x2 is distributed uniformly from 0 to 1, right? And these are statistically independent. Also, we know that, and let me just write down the conditional density of y given x1 again. So we have that piece of information. Okay, so we have this same setup, but now we're going to compute the probability of winning. We know is if y is greater than x2. So what is this expression? It's you integrate over the region where y is greater than x2 of the joint density x1, x2, y. We integrate over this region where this condition holds. That's what the probability of winning actually means in terms of the joint density. But there's a problem. We're not given this, right? Not given. So what can we do to simplify the problem? Well, we can take f sub x1, x2, y, and we can apply chain rule. So we'll do f sub y given x1 and x2. Oops, I need to erase. Of y given x1 and x2 times the joint density of x1 x1 and x2. And we know that x1 and x2 are statistically independent, so we can take this guy and we can write it as we can factorize it as the marginals. And we know something about this conditional density as well. How can we simplify that? Anybody know? You don't need x2, so you can just use the conditional density we already have found. Because y and x2 are statistically independent. So now we can use that simplified trick, and we also know something about the range of y's and x1's. We know that we require y to be greater than or equal to x2. We also know that y must be greater than or equal to 0 and less than or equal to x1. This implies that y must be between x1 and x2. This chain of inequalities also implies that for our triple integral, x1 must be less than or equal to x2. So finally, we have all the bounds on our variables we need to solve the triple integral. So I'll write out that expression. So the probability that y is greater than x2 is equal to the triple integral from 0 to 1, from 0 to x1, x1, and then we'll do dy, I'll group them like dy, dx2, dx1. So for y, it must be between x, oops, I wrote this backwards. This is x2, this is x1. Yeah, so I'll flip this as well. So we'll integrate this from x2 to x1 of 1 over x1 times 1 times 1 dy dx2 dx1. So this is the conditional density of y given x1. This is f sub x1, f sub x2. And if you solve this by hand, it's not too hard of an integral to solve. This is simple multivariable calculus problem, but it's kind of tedious, and you end up getting a quarter. And I'll show you how to solve this in Sympy right now too. So let's go. Okay, can make it bigger. All right, so let's solve the double roulette wheel problem. I'll finish the take one way first too. So I'll do both integrals in Sympy. So let's set up for double roulette problem. Let's finish the take one way first so you can see how to solve that in Sympy. So we need x1, x2, and y. So we need to bring in our symbols. So to do that, right, you just put in the string comma separated. I don't even think you need to use comma separated, but I like doing that. So you bring in your symbols, and now, once we do that, we can find what's our probability of winning. Is equal to the integrate the expression 1 minus x2. So this is the CDF way we did. I just want to show you that so you can see Sympy in action. Log of x2. And we integrated the variable x2 from 0 to 1. So this is a handy little tool. So let's print out the probability of winning. Damn it. Quarter. So that's kind of a good feeling that your math checks the code. All right, so let's do the take two. Let's solve take two now. So again, we can reuse this because it's the same variables. The only thing that's going to change is the what we're integrating. So for this, right, let's just define some function as 1 over x1, which is what we're integrating. And then let's assign the result of the integration to some variable called res. So let's integrate this f. So we're gonna have 3 tuples. We're gonna first integrate over y from x2 to x1. So we're using our symbols. And then we're going to integrate over x2 variable from 0 to x1. And then we're going to integrate out the x1 variable from 0 to 1. And let's print out the result. Print the probability the player wins equals res. Okay, so that's 2 ways of solving the same problem. The second way, we just work with the joint density directly and solve a triple integral. The first way, we apply total probability twice. So now we'll start. First we'll have a couple slides on Bayes' rule for point conditioning, and then we'll do one more example for today. So let's go. Okay. Plenty of time. Okay. To calculate the conditional density for x given y, we can apply 13, which I think was our chain rule, to the definition of f sub x given y to get this expression. So f sub x given y equals the conditional density f sub y given x times the marginal density for x over the marginal density for y. And this should look very familiar to you all because it's analogous to the probability definitions. So then we can apply 15, which was our total probability for point conditioning, to arrive at Bayes' rule for point conditioning, which is this expression. And I want you to note that these are like the likelihoods. And this right here is like your a prioris. And this right here is like your a posteriori. They're like them, but they're densities now, so it's a little bit different. So we're working with continuous random variables rather than discrete sample spaces with equally likely outcomes, but they hold the same. And then for this bottom with this integral, which is really f sub y, the density, marginal density for y, just don't ever cancel them. Like, you might be tempted to. And if you want, you could use like a dummy variable here, like new, to make sure you're not tempted to like just cancel them. So that's Bayes' rule for point conditioning. All right, so we're on to the last example for today, which is going to apply this Bayes' rule for point conditioning. So let's explain the setup. So let's let x be a uniform random variable on 0 to 1. And given x equals little x, y, this random variable y, is an exponential random variable with parameter little x. So if y equals little y is observed, find the map estimate for x. So this is the setup we have. We have something like this. We have x, which is input into a system with noise. And we get a observation y out. This is your noisy observation. This is the thing we care about. We want to know. We want to know what this is, but we don't. So let's break down these parts. What is this? So we have x is distributed uniformly on 0 to 1. And we have f sub y given x right here. This is distributed exponential with parameter little x. But what are these guys? What are these right here? Each of these. Based on our vocabulary, what would we call these? What is the a priori?
Likelihood.
And likelihood. Yes. So we're going to use those. So this right here, find the map estimate for x. This is asking us to find the map estimate, which equals the argmax over f sub x given y. But we don't have this from the problem. We have our likelihood, f sub y given x. So given we know the input, we have a conditional density of the output, y given x, but we don't have f sub the reverse. So we will take this and we'll write it as f sub x given y equals f sub y given x times f sub x divided by f sub y of little y. And we have everything on the numerator, but on the denominator, we'll just apply total probability to it. So let's take that integral to the next page. So f sub y given x, f sub x. So we know what this is, so we can simplify. And we know the range of x is from 0 to 1. So that simplifies things as well. So we have x e to the minus xy times 1 dx. And again, like you may not know how to integrate this, so you could use Sympy or integrate by parts. But this ends up being this ends up being 1 minus e to the minus y minus y e to the minus y over y squared. So this is our marginal density for y. So if we go back here, We're going to substitute this in, substitute in our likelihood, substitute in our prior, and that'll give us our posteriori density. So f sub x given y equals x e to the minus x y times 1 over, but I'll flip it. I'll just do y squared 1 minus e to the minus y minus 1 minus e to the minus y minus y e to the minus y. But this whole part right here, right, note that no dependence on x. There's no dependence on x. And we want to find the x that maximizes the a posteriori density. So what we need to do is just optimize this expression. So we need to take the derivative with respect to x of x given y and set it equal to 0. But all that stuff over there, what we just found, the denominator, doesn't matter, like for this problem. So let's apply this derivative to this. We just need to take the derivative of this, which is 1 e to the minus xy, derivative with respect to x, minus xy e to the minus xy equals 0. We can cancel that and that. So we end up with the decision rule. Of, so you move xy to the other side, divide by y. 1 over y for y less than or equal to 1, and 1 for y, or excuse me, y greater than or equal to 1, and 1 for y less than 1. So now I'll go back to Sympy, and we'll solve this problem. We'll solve this problem using Sympy. And then we'll do some plotting so you can understand the decision rule better. We'll compare some different likelihoods so you can see what's going on. Okay. So for the map estimation integral, let's turn this to Markdown. We need our symbols x and y. And let's define some function, call it func, equals x times x to the minus x times y. And let's store the result of the integration in res variable. Just want you to see this integration capability on another function, get some practice with it. We're going to integrate x from 0 to 1, so carry out our integral. And let's just print res. So we get the same answer, but they have this split into this two parts. If you add the parts, you get the same thing, but they also give a condition. They say if y is greater than minus infinity and y is less than infinity and not equal to 0, it's that otherwise, so at the point y equals 0, they give you that it's 1/2, which is nice as well. So you'd have to use L'Hopital's rule because you have this weird limiting behavior. So that's that. I think we can display it a little bit better too. I'm going to try this real quick. From IPython.display, if we import the display function, let's see if it like cleans up the LaTeX a little bit. I'm going to try that here. Oh yeah, look at that. That's pretty. All right. Now let's compare some likelihoods from this last problem so you can get more insight into seeing what's actually going on. So for now we need to bring in the NumPy package, and I'll bring in the matplotlib package as well. Let me create some more cells so I have some space to work with. So to compare different likelihoods, we'll compare from different starting values x. So I'll create this little array of x's. Not a large array. We'll start at 0 a quarter, and we'll go up to 1 and steps of a quarter. And then I'll just print that so you can see, like, okay. Next, let's create our y values we want to scan over. So let's just do y from 0 to 10. So these are our observations. These are what we see at the output of the noisy system. 10, and let's do 100 points. So next, let's create an array to hold our likelihoods. And now we'll populate this with our actual likelihoods for each starting x. And for I comma x, n enumerate x's. What we'll do is we'll store that. So now we'll create a plot, and you'll see from different x's, like what density is maximized. So what x is the map estimate. So let's create a figure. Do plt.plot y versus the likelihoods. And let's use a red solid line and label it x equals 0.25. I need to show it. So let's add some more to here. Let's add the rest of our points. Oh my God, did I just delete that? Sorry about that. Likelihoods. X 0.25. PLT.show. All right. Let's change these. Let's use green. Oh my God, come on. Let's use a green line black line, a blue line, and a black line. Change this. Nice. And so we can add a little bit more to our plot. I don't know how familiar y'all are with Matplotlib, but I'm sure you've gotten more familiar over this semester. But we can add some more to like decorate our plot. So we can add a legend, which will add the label information I wrote there. Then we can add a X label, which for us is Y. Then we can actually insert some LaTeX into the labels as well. The R means raw string. And to use LaTeX in here, you need to use dollar symbol. Y given X of Y, little y given X. And then enclose it in dollar symbol. And then we'll add a title. Likelihoods. Now if we show this, it looks a lot better. So the main thing I want you to see is that with x equals 1, it dominates all the other likelihoods up till the point 1. So that's where the decision rule comes from. So for y is less than or equal to 1, you always decide x equals 1. And then below, for y is greater than or equal to 1, x will be 1 over y. And you can check that. But one other thing I want to plot is we can plot the decision rule. So for that, all right, we have our y's. So we just need our decisions. And for this, I'll use a list comprehension. So 1 if val is less than or equal to 1, else 1 over val for val and y. And then we can create a figure for this to plot our decision rule, our map decision rule. And again, plt.x label is y, but plt.y label, we will do some LaTeX again. You can use a hat symbol for your x estimate, and then in LaTeX for a subscript, you just do the underscore, and then put it in curly braces map. Enclose everything in dollar signs. And then we'll add a title, plt.title, map decision rule. And then we'll show it. So that's the map decision rule. So all right. That's all I've got for today. It's end of lecture.